Physics chapter 28 theory video 1 we are going to learn about quantum physics. So this is actually one of the key parts of physics, and this is something that is still all the parts or many of the parts of physics we are still trying to understand. There are many things for us to learn about this and also to develop. So but we have come a long way since Albert Einstein developed the certain equations to understand the underlying principles of quantum physics and quantum mechanics. But now we have advanced in a great way, but still there is a lot for us to understand. Now we know that we know that we know the difference between particles and the matter and energy, but in a different sense they collide in a different sense. That is, there is an overlap. So that is something that we are trying to understand. Light and matter, how do they model into one uniform aspect of what we learned, that is the particles and waves theory. Now we actually learn about particles, and we learn how matter is related to that, right? So for example, when we imagine particles, we think of objects that are hard and have a mass, and which obeys the Newtonian laws of mechanics. We know that when two particles collide, they will have elastic or inelastic collisions, and we can, based on their masses and how much of a velocity they would have, we can understand how they would behave. Now, for example, when you play snooker or pool, you will be able to, or even carom, you can understand how particles behave. So we say that they are a macroscopic model. So that means from what we can observe. Now when you look up at the sky, or when you are when you're dealing with different things or whatever, we can use this particle model to explain how they behave the way they do. Now when you use this particle model in things that we cannot see, that is the microscopic world, we can actually we can explain those phenomena also. Now, for example, if you take a gas, when you take a gas, if you consider them as hard, random, small particles randomly moving about and colliding haphazardly one another, and on the walls of the container, that develops the kinetic model of a gas that we have learnt earlier. So the macroscopic properties such as pressure and temperature in this can be detailed and explained using the microscopic particles and their properties. So as a result, we have actually we can develop many theories based on these models. So electricity, the model is flow of electrons. Then the macroscopic phenomena is the flow of current. Gases, we have the kinetic theory. Then the macroscopic phenomena that we can explain using that is pressure, temperature and volume of a gas. Solids, we have the crystalline materials as the model. Then mechanical properties. Then radioactivity, we have nuclear model of the atom as the model, and macroscopic phenomena that we can explain using that model is radioactive decay, fission, fusion, etc. And then in chemistry we have atomic structure. Then using atomic structure we can explain atomic chemical bonds and chemical reactions. Now, a different model that we are going to develop and discuss is wave model. Now, if you consider water, you will have you have seen different waves. They make waves when you go to the ocean. There are ranging from little ripples and the massive tsunami waves. You can have different kinds of waves, and then there are the tidal waves, and varying kind of waves are there. Then if you take the wave in physics, you have observed that is the sine graph. We don't actually see uh, the ocean, the crashing waves, but we rather see the ocean in the ocean or in water. The physics wave is actually what is in the middle, not the one that is crashing onto it, crashing onto the beach. So it is a smooth curve, a sine curve. So then now the problem here is even in physics and in the ocean, it is not just one wave that comes along. There are many waves acting up. So it is a combination of many waves, and we know that it is the principle of superposition that we have learnt earlier. So waves have a way of transferring energy from one place to another. So there has to be something that needs to change in a wave in a regular way. So the energy is traveling along. In water, the surface of the water will move up and down. It does not actually move from so this is how the water waves would be. This water actually moves up and down, not continuously like this. It moves up and down, and the energy is what transfers through. I hope that makes sense. Uh, so then the phenomena and the quantity that varies in relation to a lot of things. Let's discuss. Sound, the pressure or the density is what changes. In light, electric field strength and magnetic flux density. We will be learning a little bit further about this later on. Then waves on strings, it is a displacement, and the string itself does not move along the particles of the string does not move along the string. So these characteristic properties of waves show us reflection, refraction, diffraction, and interference. All of these things have been defined earlier. So the wave itself doesn't have any mass or charge. It is now particles. Using particles we can explain reflection and refraction. When you consider diffraction and interference, we have to be concerned thoroughly about waves, because diffraction and interference, we know that we are talking about waves. But when it comes to reflection and refraction, it might be a material or particles as well. So that is something that we have to take into consideration. So now we have learnt about waves and particles. Now how are we going to figure out which model is useful and which can explain the situation is what we have the problem about. Then light, is it particles? Now you have learnt about photons. So is it the particles that travel, or is it the energy that get transferred? So Newton, now you must be having a very good idea about how light travels. So in earlier, when we did not have all the evidence to prove otherwise, people believed that the Newton's view of light traveling as particles is what was accepted. In 1704, he wrote a book called Optics. So in this book he explained reflection and refraction. He suggested that light would travel faster in water than in air. Then in 1801, Thomas Young he showed that diffraction and interference also are part of light. So as a result, we know that particles can show reflection and refraction. So that was accepted. But when Thomas Young explained that it can also diffract and interfere, then we realized that there was a wave effect on this as well. Then in 1853, Leon Foucault, a French scientist, he showed that in water, light would travel much more slowly than in air. Then the Newtonian principle of light traveling through the space as particles had to be abandoned, and now it is the belief and understanding that light travels in the form of waves. Write down a note. Different models have been developed to explain macroscopic phenomena using the microscopic properties. And please draw this chart, table 28.1. Electricity, flow of electrons, then the macroscopic phenomena that can be explained is current, etc. So write this, then you will get a better understanding. Then write down wave model. When some characteristic is explained, using the transfer of energy through waves, wave model is taken into consideration. When waves transfer energy, some characteristic needs to change in a regular way. For example, in water waves, the surface water moves up and down while transferring the energy horizontally. Then draw table 28.2. You will understand it better when you do that. Then write down all waves show reflection, refraction, diffraction, and interference. Particle models can also explain reflection and refraction. However, diffraction and interference are characteristic of waves.
Right. So we will discuss particulate nature of light. Now we understood that the light needs to behave as waves, but we know that light has the ability of behaving like particles as well, right? So we have already discussed some parts of it. So we know that it is not only a wave but also it has the particulate nature also. Now um, uh, so if we place a Geiger counter, that is something that is an instrument that can be used to measure electromagnetic nuclear radiation. If we place it near a source of gamma radiation, we will hear that clicks. So there would be it would be measuring or detecting the gamma rays. Gamma rays are going to be part of the electromagnetic spectrum, which belongs to the same family of waves as visible lights, radio waves and X-rays. So waves in this particular situation, we can see that gamma particles or gamma rays are giving the exact similar uh, sound like the alpha particle or beta particle when they collide with the Geiger counter. So as a result, we have to assume that the gamma particles will also behave like particles when they interact with the gas particles in Geiger counter. This is actually very much clearly seen in gamma particles in the electromagnetic spectrum visible light region, because they are at the most energetic part of the electromagnetic spectrum. With the visible light, we are not we cannot show that it as easily as that. Then we come to the photons, and this is the place where Max Planck and Albert Einstein had lot to do with this. The photoelectric effect, and Einstein, and the way Einstein explained it, uh, defined. So it actually proved that Newton was also not exactly wrong. So now this proved that light can actually behave as a stream of particles as well. So uh, we call the corpuscle that was used by Newton to explain that light was what light was made up of is has been renamed, and we use photon to explain that particle. Then we say that all electromagnetic radiation consists of photons. It's a packet of energy or a quantum of electromagnetic energy. So that is what we refer to as the photon is the quantum of electromagnetic energy. Gamma photons are going to be the most energetic. Then Albert Einstein, he actually worked on the theories brought forward by Max Planck. He was a German physicist. He said the energy E of a photon in joules is related to the frequency in hertz of the electromagnetic radiation of which it is part of. That is, E equals hf. H is the H is a Planck. H is called the Planck constant, and it has an experimental value of 6.63 into 10 to the power minus 34 joules. Joule seconds rather.
or else we can use it as joules per hertz. So as a result, we can understand that the energy of a photon is directly proportional to the frequency of the electromagnetic wave. That is, E is equal to, we develop this equation using something called the Einstein relation, which relates to all electromagnetic waves, and we combine that E equals hf and show that to show that particle like property of photon and wave like property, that is the frequency, we call this relationship Einstein relation, and we use this as E equals hc upon first of all, we have to remember that the frequency f and wavelength lambda of an electromagnetic wave, they are related to the wave speed c by c equals f lambda. So then we have the equation E equals hc upon lambda, and h is the Planck constant. We had a value for that, 6.63 into 10 to the power minus 34 joules per joule second or joules per hertz, and then we have frequency and lambda, the wavelength. So the Einstein relation is going to be E equals hf and E equals hc upon lambda. So we have these equations in relation to the photon or the quantum energy or the packets of energy. So we know that photon, the energy content of a photon is inversely proportional to the wavelength, because E equals to hc upon lambda. So as a result, short wavelength X-ray is far more energetic than long wavelength photon of light. So now if we want to work out the energy of a gamma photon, we know that gamma rays have frequencies greater than 10 to the power 20 hertz. So as a result, we know that gamma photons would have energy that is 6.63 into 10 to the power minus 34 into 10 to the power 20. So that is going to be 10 to the power minus 13 joules. Now if you take a single gamma photon, this is a very tiny minuscule amount of energy. So when high energy gamma rays go through these astronauts' eyes, why don't we experience that? Because these gamma rays are blocked by the thick atmosphere that we have. Or they are, they are not exactly blocked, but they are, they are reflected rather. So these astronauts have said that they have felt when the individual cosmic rays, high energy gamma photons, when they pass through their eyeballs, they have seen flashes of light. So now when we take a light emitting diode, even though the amount of energy that is contained in a photon is small, but the amount of photons, the rate at which photons are emitted, can be huge. So that will be explained in this worked example. We will see what happens here. So they say a light emitting diode emits light of wavelength 670 nanometers. The radiant power of the light from the LED is 50 millivolts. Calculate the rate at which photons are emitted from this LED. So what we need to do is, we have to find out how much energy is given out by a single photon. So energy is hc upon lambda. So all the details are here. 6.63, that is the Planck constant, into 10 to the power 34, multiplied by c is 3 into 10 to the power 8 speed of light divided by lambda has been given wavelength 600 nanometers, that is 670 into 10 to the power minus 9. So that means 2.97 into 10 to the power minus 19 joules is the energy of a single photon. Now to find the rate at which the photons are emitted, we know that the rate at which photons are emitted is the number of photons emitted per second. That is power divided by energy of a single photon. Power has been given as 5 into 10 to the power minus 5 into 10 to the power minus 4, then that is 15 to 10 to the power minus 3. Then you divide that by 2.97 into 10 to the power minus 19, so that would give you 1.6 into 10 to the power 17 per second. That means per second 1.68 into 10 to the power 17 photons are emitted by this single LED. I hope that makes sense and you understand how to do these questions. Write down. When gamma rays, which belongs to the same family of waves as visible light, is passed through a Geiger counter, it gives out the tick sounds that we get when it passes through. However, according to the wave theory alone, this cannot be, because gamma rays are waves and would not have particulate property. However, this proves that that theory is wrong. And visible light and gamma rays are made up of particles. These particles are now known as photons, which is a packet of energy or a quantum of electromagnetic energy. The amount of energy of a photon is equal to E equals hf. H is known as the Planck constant and has a value of 6.63 into 10 to the power minus 34 joules seconds. As a result, we can understand that energy is directly proportional to the frequency. The equation E equals hf defines how
photons have the particle like property as well as the wave like property. This equation can be written in relevance to C equals F lambda as well. Right, and then write down the Einstein relation E equals HF and E equals HC upon lambda. I hope you understood. If you did understand, please do the questions 1, 2, 3, 4, and after that we will go to the next video.